Ladies and gentlemen, welcome very warmly to this webinar of the World Bioenergy Association. Our webinar is going to deal with the role of bioenergy for flexibility in energy systems. And today we will cover the demand for heat. Maybe some of you have participated in our last webinar, which was dedicated to the role of bioenergy to provide flexible electricity. Today, we are going to talk about the role of bioenergy for flexibility in heat provision. Before we go right into the topic, let me just share a few things about our organization, the World Bioenergy Association. We are a membership organization with a global outreach. We have members both in the field of business, in the field of policy advice. We have members from diverse associations across the world that are dealing with bioenergy. We try to be active in sharing knowledge on bioenergy. We are publishing global statistics. We're engaging in partnerships with other organizations. And we try to advocate for the use of for the sustainable use of bioenergy. Maybe just a word of invitation. Next slide, please. Join our community. We are steadily enlarging our membership base. Please feel cordially invited to come on board, to become a member of the World Bioenergy Association, to either become speaker at some of our events, to join our delegations to high-level forums such as the climate conference. You can publish together with us publications, participate in working groups, or simply support advocacy for sustainable bioenergy. So that's a warm invitation. Please consider that and feel free to contact me at any time in that context. Now let's talk about our webinar today. We have a lineup of excellent experts that will look at different ways of providing heat, about different needs for heat, needs, for example, of entire cities in the Northern Hemisphere for heat, needs of industry for heat, but also domestic needs for either heating or for cooking, and how bioenergy can play a role in these fundamental human needs. Before we kick off with the first speaker, just two words, because we very frequently get questions about, will the slides be available? The answer is yes. We will publish the slides on our website, so you are also able to see all the recordings of our past webinars on our website. Within the next 2 or 3 days, they will be online and you will be able to use them. So if you have questions, please feel free to use the chat. Put up your questions there and we will try to answer the questions after each speaker. So if you have a question to what has been presented, we'll try to give you the answer right after the presentation. Yes, and that leaves me basically to ask Shell Anderson to come to the floor. Shell is with the IEA Bioenergy Task 44, which is dealing on flexible bioenergy and system integration, research cooperation, and international research cooperation. Shell, the floor is yours.
Thank you. Can you see my slides?
Yes, we can. Just
I'm going to put them in here.
Perfect.
Yes. So my name is Kjell Andersson. I have worked with the Swedish Bioenergy Association for about 20 years as a policy director, and I've also been active in Bioenergy Europe, with sustainability issues. But this time I'm going to speak about bio-based district heating. And I work as a national team leader for Sweden within the global cooperation in IEA Bioenergy Task 44, as Christian already mentioned. What is flexible bioenergy? In this Task 44, we have tried to make a definition of this. We say that it is a bioenergy system that can provide multiple services and benefits to the energy system under varying operating conditions and/or loads. We are talking about flexibility from seconds, which can be, to support the power grid. We talked about that a couple of weeks ago at the other webinar, up to seasons, which is more typical for heating, that you can have flexibility between summer and winter, for example. These are some of the examples of flexibility that we work on. We work on technologies and concepts providing grid stability for power systems. We already talked about that. We have more and more wind and solar, and then bioenergy can be a balancing factor. Because bioenergy is dispatchable production of energy, and this can be used then according to market demand. This is typical of bioenergy systems. We have also work on integrated polygeneration systems, combining production of heat, power, fuels, and/or chemicals. I'm going to give one example later on in my presentation connected to district heating. We talk about long-term storage options, such as biofuels and biochemicals, and other services to the system, ancillary system. This is a rather complex picture, and I'm not going to go through it, but I just show it to show you that bioenergy is not, it's both complex and it's simple. We use biomass, different kinds of biomass for different chemical processes and combustion, and then we end up with a number of different applications. But there are so many pathways within the bioenergy system that also offers many different options and possibilities. We have flexibility in almost all of these stages of the process. We have flexibility from different kinds of feedstocks. We have different kinds of intermediates and energy carriers that also offers a lot of flexibility. And we have a number of different applications. Chemicals, transport, and mobility, and we are now going to talk mainly about heat, and heat also means storage of energy, and heat can also be produced together with power, and then we have combined heat and power plants, for example. This all looks very complex, but it is also, as I said, in many ways simple. Above all, we have to remember that bioenergy in itself is stored energy. We have a storage of energy in the fuel itself, in the chips or in the pellets or in the different kinds of energy carriers like methane or like biocoal, for example. But and this storage is also already very much established technology, and it is cost efficient, and it doesn't have any big losses. It's very stable energy. You just put it all in a big pile or in a container, and it stays there for quite some time. Now I'm going to talk about bio-based district heating. So this is large-scale use of bioenergy for heating in grids that connect hundreds or thousands of houses, buildings, and industries to a common grid, and then it's supplied by one big heat plant or a boiler. And it isn't only for the northern hemisphere, actually. Like Christian said, you can also make these grids for cooling. So it's both about heating and about cooling. So it is a global kind of technology. In Sweden, we have about 560 of these heat plants in our 290 municipalities that use biomass and biogenic waste. On this map, you can see the red is biomass and the orange is municipal waste in all these different cities. Biomass accounts for about 70% of the fuel supply. We almost don't use any fossil fuels today in our district heating grids. And we can also produce about 4,300 megawatts of electricity in our combined heat and power plants. This is in the 90 bigger cities that we can use this. During the last 20 to 30 years, we have converted almost all of these grids from fossil fuels over to biomass or municipal waste. And as a result, the emissions of CO2, carbon dioxide, from our heat production has decreased drastically, down to just a small fraction of what it used to be some decades ago. And the remaining part there is almost entirely from fossil plastics in municipal waste. Sweden isn't the only country that has done this. And it isn't only in, like I said, in the northernmost part of Europe, but our neighbor across the Baltic, Lithuania, is a good example of what can be done in almost any country where you have municipal waste and you have biomass. They have converted all of their heavy fuel oil and natural gas during these last 20, 30 years, or 20 years or less, over to biomass, and they have opened a number of large heat plants to do this. And also district heating is not, as I said, only in Northern Europe. It is actually available in very large parts of the European Union, particularly in Central Europe and East Europe. And like you can see here, countries like Poland, the Czech Republic, Hungary, and so forth, beside the Scandinavian countries and the Baltic countries. I think Denmark is probably the countries with the highest share of district heating. And the possibility is still, there is still quite a large potential to increase the use of district heating in Europe. What is the multiple ways to provide flexibility in biomass-based district heating? I have summarized this here in a couple of slides. With combined heat and power in district heating, you can provide both electricity and heat on demand, and you can respond to price changes. Electricity can be provided to the grid for balancing and peak load. The power output can be increased using gas turbines or other modern technologies. We talked about this at the other webinar. By using hot water accumulators, energy and heat, the heat can be stored for days, maybe up to weeks, and the boilers can be used in a more optimal way. This is an important flexibility issue. Seasonal storage is possible, but it is still not cost effective. But we can combine, for example, solar energy in the summer with biomass in the winter. We have some good examples of this on our website on T44. You can go there and look at that. For example, in small communities in Germany, but also some of the bigger district heating grids are more and more using solar energy too. Other forms of energy can be produced, like pyrolysis oil, methane, pellets, or steam at high temperature that can be used for the industry. And the grids also open up for use of surplus heat from industries and also from other energy sources. I'm going to show a couple of examples at the end here. This one is a combined heat and power plant combined with the pellets production. Is from Falun. It's a city in middle Sweden. And at this plant, they have docked a pellets plant to the CHP. And they also have waste heat from a data center nearby, and they have a big hot water accumulator. And this way they can optimize the use of the heat and the production of electricity to the times when they have the biggest demand for electricity. And by producing pellets and using the dryers, they can extend the running time for the turbines in the combined heat and power plant. So this is an example of how you can optimize by using multiple systems together, systems integration that we talk about in T44. And this is a picture of how the whole system works. It's not simple, but it's it is very efficient. And you can see up in the left-hand corner that they also have a connection to a waste to heat CHP in the nearby city of Borlänge. So two cities are working together, which also increases the flexibility for both of these cities. This is an example of a hot water accumulator in the city of Linköping. And you can see the numbers here. They can store up to 1.4 gigawatt hours of hot water. It holds 30,000 cubic meters of water. And you can see the capacities there in the numbers. You can look at the slides afterwards. And this is an example of how you can use the CHP for flexible power production. This was in 2022, a very mild winter. And so the prices of electricity were relatively low in Scandinavia. But then all of a sudden in September, the electricity prices went up. This was during also caused by the general energy crisis in Europe. And they were able then to use the turbines in the combined heat and power plant, despite the fact that the heating season hadn't really started yet. So you can use these turbines then in a flexible manner, but then you need to have the heat system or the grid to be able to have these plants up and running. That was my last slide. And if you have any questions, I will be happy to answer them. Of course, this is a huge subject, and there are numerous issues to cover within this area.
Many thanks, Kjell. Yes, there is a question, and that is, why are Western European countries using less bio-based heating than Eastern? Is it just the availability of wood? And what happens to the CO2 emissions from bio-based heating in Sweden?
I think there is, what should I say, political answer to this. District heating is a sort of common good collective solution that has been furthered, for example, in the East Bloc countries and also in the Scandinavian countries, where there has been a bigger openness to collective solutions, doing things together by the cities and the communities, where the West European countries maybe have had a more individualistic view on how to solve these things. I think also maybe in the later years, the availability of natural gas for heating, for example, and the gas grids have been detrimental to the expansion of district heating. This could be one example of this too. I don't know how to answer it otherwise, but it's in general, you know, how the energy systems are designed in different countries varies quite a lot from country to country. There is almost no district heating in Norway, for example, but the reason is that they have an abundance of hydropower. So they have a lot of electric heating in Norwegian homes. Whereas on the other hand, Denmark has no hydropower. And so district heating has been a very much favored solution to heating their towns and cities. Yeah, that would be my answer.
And there was a second part of the question that was, regarding the CO2 emissions from bio-based heating. Can you comment on that?
Well, the CO2 emissions in bio-based heating is part of the natural green flow of CO2 between plants and combustion. It is carbon neutral. So that is no problem, of course. On the other hand, it offers today new possibilities because we can use this CO2. We can capture it, at least in the larger plants, and eventually use it for bio-CCS and store the carbon dioxide. And in that case, we get negative emissions, and these heat plants can be used to reduce the content of CO2 in the atmosphere.
Yes, we had actually a webinar on that subject. Please feel free to look at that. And there is a final question, Shell, for you, which is, which method can produce higher amounts of electricity from biomass, pyrolysis or gasification? Which method has reduced CO2 emissions?
Well, the CO2 emission issue is, as I said, not an issue for if you have a bio-based CHP. But which one is more pyrolysis and gasification? I mean, there's similar kinds of technologies. I think this depends very much on how these plants are designed from the beginning, and how you can rebuild them or develop them. If you have an existing plant, or if you're building a new plant, for example, if there is a demand for this pyrolysis oil, for example, gasification can help to increase the alpha value drastically if you can use it in a smart way. There are several projects to work on this. But finally, it's usually an issue of economy for the single utility, what they can do.
Well, we have a comment here. Combustion is the best, I think, says An Soyoung. And I would agree with that. I mean, if you look to Sweden, all of your CHP plants are simply combustion plants. None of them are gasification plants, and none have anything to do with pyrolysis oil. I mean, to be quite honest, I mean, particularly pyrolysis oil has not seen a commercial application anywhere in the world so far, has it?
Oh, we have one pyrolysis plant at a sawmill. They are producing from sawdust. That's an example. I mean, they're working on it, and there is also in IEA Bioenergy a certain task that works on this issue. But of course, combustion is a simple technology. The Swedish plants, almost all of them have flue gas condensation, which means that the efficiency is much higher than in a regular combustion plant. And then the next step, I think, would be BECCS, bio-CCS, to capture the CO2. So that will make these plants even better.
Thank you very much, Shell. And that takes us to our second speaker. Johannes Schmiedl is an energy expert from Austria. He has been working with the Austrian Energy Agency and later with the Austrian Pellet Industry Association. Hannes, you are going to show us a little bit how the interplay is within the entire energy system between heat markets and the electricity markets. Floor is yours, Hannes. You're still muted. You're still muted.
Now, does it work now?
Now it works.
Okay.
So please share your slide.
Okay, sorry for the late start. My name is Johannes Schmiedl. I'm working for the Austrian Association of the Pellet Industry, ProPellets Austria. This is the association of pellet producers, stove and boiler producers, and pellet supply and logistic organizations and associations. And I'm talking about the energy for the heat market in Austria and the ignored aspects of power and storage. You may be aware of the graphical representation I'm showing here, a pie chart.
Please share the slides, Hannes.
Okay, can you see it?
Not for the moment.
Okay. I did share the slides from.
Alejandra, can you jump in and share the slides from our side? Ah, here they are. Very good. Okay.
I hope you can see the second slide. Now, energy supply is not a pie.
Yes, we can.
Okay. Maybe you are used to this kind of representation. It's a graphical representation of energy demand. You will be accustomed to it, but it is only part of the truth. This kind of representation provides an image of an average demand of the year, insinuating a smooth demand curve. You can see the energy demand of Austria, final energy. You can see heating and hot water are about 1/3 of energy demand. Austria is a country situated in a cold climate. We have a lot of heating during winter time. Process heat is 18%. So heat together amount for about half of our energy demand. Traffic and transport for 1/3 roughly. And there are some minor lighting and electronics and stationary engines. Altogether, about 50% of the energy is used for heat, and about 22% of the final energy demand is electricity. So next slide. This is a more realistic picture of the energy demand. This you can see from January 1st to December 31st, a whole year, this year 2017, the daily peak and lowest load in the electricity grid in Austria. You can clearly see the weekends. During the weekends, Saturday and Sunday, the demand is usually lower than over the week because people are not working so much. And what's also important, the highest load in the electricity grid in Austria is about 10.5 gigawatt, 10,600 megawatts maximum power. And it occurs during the coldest period of the year. We are starting on the left side of the x-axis with January. During January, usually we have the lowest temperatures in Austria, and the demand is going down during summer, and it climbs up again in November and December. The highest power demand occurs in the coldest period of the year, 10.6 gigawatt. The lowest load was in August with only 4 gigawatt. And you can also see a daily spread of about 4.2 gigawatt. The spread is the area between the highest and the lowest demand of electricity. This is electricity. Now I switch to another picture you will not be accustomed to. And this is the time variation curve of the heat demand in Austria. And I will start with this red line, which again goes from January 1st on the left side to December 31st on the right side. And the red curve in the lower part of this picture is the daily electric peak load. You can see the highest load was, like you have seen before, 10.6 gigawatt in January. But in this presentation, you can also see the heat demand running from January 1st to December 31st over the whole year of 2017. Again, the heat demand depending on different energy carriers. There's something like a base load from natural gas, biogas fuels in industry, and also some oil in industry. And there is a load coming from heating and hot water preparation in the households. And you can see this load is climbing up to almost just above 50 gigawatts, meaning 5 times the peak load the electric grid in Austria does provide. So the maximum power demand in the electricity grid is 10.6 gigawatt, and the maximum demand in the maximum heat demand is about 50 gigawatts. So there is a factor of 5 between the power which is provided by the electric grid and by the which is demanded for heat. So I think this is a rather important picture, and it's more precise than the usual presentation in form of pie charts. The next slide shows the possibilities to store energy, at least some of the possibilities to store energy, and maybe the most prominent. The picture on the right side is something which is used in mountainous countries all over the world. It's called pump storage. You build lakes up in the mountains, and you can pump up the water elevations of almost 1,000 meters, and you can, this is kind of a mechanical storage device. When electricity is cheap, for example, a lot of PV or wind, you can pump up the storage, the water in the mountains, and if you need electricity, you can release it and let the water run down, and you produce, you transfer the mechanical energy to electric energy, and you can feed it into the grid. On the left side of the picture, you have 2 bars. The right bar shows the amount, the storage capacity of all the pump storage plants in Austria, and there really are a lot, and their whole capacity is about 4 terawatt hours. So if you would fill them completely and let the water run down, you would generate about 4 terawatt hours of electric energy. The small black part of the bar on the right side of the picture is an energy storage system which is not yet in place. If you would convert the whole fleet of Austrian passenger cars, there are about 5 million cars running in Austria. If you would convert the whole fleet to electric cars with a 100 kilowatt hour battery in each of the cars, you would produce an additional storage capacity of 0.5 terawatt hours. That's the right side of the graphic of the 2 bars. On the left side, you see, I can see a much bigger bar. This is the storage capacity of biomass in Austria. Again, starting from bottom, the some 200,000 pellet boilers which are in place in Austria can store energy in the form of pellets close to them, and their capacity is almost the same amount, 4 terawatt hours, as the whole fleet of pump storage systems in Austria. So we have about 4 terawatt hours of stored pellets. However, we have also storage capacity in form of logwood and of wood waste, and all together they amount to about 30 terawatt hours of storage of energy storage systems in Austria. This is quite a high amount of storage, and this, in the discussion, it's in my perception frequently ignored because everybody's looking at batteries, accumulators, and at pump storage systems. I come to my conclusions, and it will be clear for you, but it's not clear for many people present in the energy system. Also for journalists, electricity is energy, but not all energy is electricity. Energy demand over the year is not a smooth curve over time. This is very important. And the energy, the supply of a country cannot be presented in a pie chart. This is only a very small part of the truth. And the ups and downs of energy demand in industry and households follow a varying curve. And the main trigger of low temperature heat demand follows the pattern of heating degree days, meaning the outside temperature. The power demand for heat outnumbers the power provided by the electric grid, in the case of Austria, by a factor of 5. And this may be quite similar in other countries which have a cold climate and a lot of heating. And the bottleneck capacity of the electric grid will not be able to supply the heat demand because it would fail both on the side of the grid and on the side of the production capacity, especially in winter. And if you would switch the heat supply completely to heat pumps, the COP, you know, this is the coefficient of performance of a heat pump. This is the relation of heat output to electricity input. Of course, it would lower the electric demand, but especially during the very cold days in winter, the heat pumps operating with the ambient air have a COP below 2, and it's approaching 1, so the electricity demand would not be significantly lowered. And so I come to my most important conclusion that biomass is a storable renewable energy carrier which can supply high power during short time periods, is deeply needed in our energy systems. Thank you for your interest.
You're on mute, Christian.
Thank
Hello,
you. Thank you, Jawahar. Yes, thank you, Hannes. That was, I think, a very important contribution because after spending many years in the energy field, my perception is that the confusion that electricity is energy and that's all, that's the whole story, is still very widespread. Usually when people talk about energy, they mean electricity, and they believe electricity is all that matters when it comes to energy. And obviously this is not the case. As you mentioned, it's just a bit more than 20, maybe in some cases 30% of the energy demand, and the rest is heat, is transport fuels, and that's where bioenergy can play an important role, as you have shown. And that leads me to our next speaker, and that is Jawahar. He is from Berkeley Energy Commercial Industrial Solutions, operating in 7 Asian countries. Jawahar, your company is especially providing heat services, but also other energy services in the industry. Please tell us about your story.
Thanks, Christian. I'm going to pull up my slides. Okay, good afternoon, everybody. Good morning and good afternoon. So my name is Jawahar. I'm from BECIS, or what's known as Berkeley Energy Commercial Industrial Solutions. And today I'm going to be talking a little bit about bioenergy and its application in the industrial heating segment. So just to give you a small update about what we do, we are basically energy as a service company. We operate in 8 countries in Southeast Asia, India, and China. Our model is basically around providing energy as a service on the build, own, operate model. And we work with most of the customers, and quite a few of them being large MNCs, helping them to actually decarbonize their energy. As a company, we do provide different kinds of solutions. We have in our portfolio both solar as well as bioenergy, and we also provide other solutions on cooling as a service, and some of the other things that we're working on is basically on biogas and e-mobility. So this is just a quick update about us. I'm going to go directly into giving you some insight in terms of what energy as a service means. So basically, we look at industrial customers and we try to understand what is their current energy demand. And then we try and map that with respect to what kind of renewable energy solution that we can provide to them, which helps them not only to optimize their energy costs, but also helps them to reduce their carbon footprint. And all of this is done on energy as a service model, where we take care of the complete development of the asset and then running the asset and then providing the energy to the client as a service. The different types of solutions we offer are, as mentioned in the table, but today we're going to talk a little bit about bioenergy. So basically, we are helping our clients, reduce their CO2 emissions by replacing their fossil fuels with a more sustainable and renewable source of energy. And this is basically to generate either electricity or heating or cooling, depending on the needs of their plant. And all of this is done through a build, own, operate, and transfer model. Just to set the context, as most of us are aware, a large part of the greenhouse gas emissions which are coming out is also being contributed by the industry. Almost 25% of that, which is going to the energy needs of the industry, are coming from industrial production, apart from the other sectors like transport and using it for district heating. So this is where I guess a lot of the GHG emissions are coming from use of fossil fuel. And our endeavor is actually to help reduce that by using more renewable source of energy. I think, as most of us are aware, a large part of the industry, especially the multinationals, have taken, their net zero commitments and hence are moving towards more renewable source of energy. And this is something that's documented in public domain, and we see that trend happening in the markets as well. So I'm going to talk a little bit about how we approach in terms of designing a renewable energy solution, or more specifically a bioenergy solution. So the approach that we normally have in terms of industrial clients is to first understand what is their energy demand and how is it mapped with respect to their carbon footprint. And basis that, we then start looking in terms of what kind of a renewable energy solution can we actually put in place. This could be either standalone solutions, or we could integrate multiple solutions to actually give them a kind of a package which will help them optimize their carbon footprint and give them the maximum CO2 penetration that they want to achieve. And of course, we also need to take into consideration at what cost does this solution actually come to them. So the approach, if we do a little bit of mapping, we will find across various solutions that the maximum impact from a CO2 reduction perspective is actually coming from the bioenergy solutions, and to some extent maybe extended solutions on the biogas and the compressed biogas solutions. The financial savings, of course, may vary from country to country and sometimes within the same country from one location to the other. But when we look at both these perspectives, both from a financial perspective as well as the GHG reduction perspective, bioenergy comes out clearly as one of the solutions which can give a maximum impact to the clients. So if we look at a typical demand, energy demand in an industrial application, as you know, in the manufacturing process, the industry needs basically heating, also requires cooling. They also require power and compressed air. So broadly, if you look at all these 4 utilities, they form the majority energy demand for any process or any manufacturing industries. What are the key challenges that we face when we look at either a selection or design of a bioenergy solution for an industrial application? So I think one of the major problems that we face is the assessment of the thermal demand, especially when you want to map it over a period of time. This is because in many of the industries, the clients don't have the data with them. Either they've not invested into equipments or monitoring devices, or they just have not captured the data to give us that kind of information to make a decent assessment on what is the energy demand. Second is most manufacturing plants have a very fluctuating demand. It's either coming because of their product mix, what they manufacture in the plant, or the market demand for their products. Or in most cases, we found that the plants are designed for a higher capacity, but operating at a much lower capacity. Another challenge is obviously trying to see what is the thermal versus the electric demand. This is very important to understand whether we need to go in for separate thermal systems or go in for a cogeneration or a CHP plant. And sometimes this mapping is also very difficult due to lack of information from the client side. Many a times we see that there's a mismatch between the power and electricity demand, making it a big challenge to decide what's the best approach to provide the client. The grid electricity cost and the fossil fuel cost in a specific geography is also one of the criteria that need to be considered before deciding on the kind of solution. Bioenergy plants, as we know, require a lot of space, and in many cases in a manufacturing industry, availability of space is a big constraint. We also need to look at what is the availability of feedstock at a reasonable distance, because logistic cost is obviously the biggest element in the feedstock cost. And then last but not the least is the biomass security and the cost fluctuation, which happens over a period of time when you put up these bioenergy plants. So some of the design criteria that we look at when we put up a bioenergy facility is actually what kind of fuel flexibility do we need to build in. We obviously need fuel security when we're putting up these plants in an extended life cycle. We also need to look at the process plant requirement in terms of their pressure demand and the fluctuation on the pressure side. Some of the plants also have quality requirements in terms of the type of steam that we can generate, either for culinary applications or for other applications which go into either the pharmaceutical industries or the F&B industries. The safety compliances that are non-compromisable in any of these plants, I think we need to keep that in mind when we put up these kind of systems. And of course, we need to look at the emission compliances specific to a particular geography where we are putting up the plant. So some of the bioenergy options which we commonly come across, and this is something that we have studied and over a period of time, and we have been providing these solutions. One is, of course, to generate steam using agricultural biomass, which is available in abundance in many of the countries, and generating either steam for their process application or for steam to generate power, or a combination in a CHP plant. And in certain cases also to generate steam to use it for cooling through absorption chillers. The other solution that could be done is to actually use agricultural biomass or other waste to generate biogas, which could be either used in the boilers to generate steam, or it could be converted into biomethane. So some of the solutions that we thought seems fit and apt for the fluctuating energy demands in a processing plant is basically using of biomass to generate steam and supplying it for their thermal energy requirement, as well as for their electricity generation. And the other solution is, of course, using the agricultural waste or other organic waste to generate biogas, use it in a boiler to generate steam, or convert it into biomethane, which can be used for either power generation or for generating heat energy. The advantages, of course, using the bioenergies, it works on a circular economy where all the agriculture biomass which is utilized in the boilers to generate either heat or electricity or cooling is then subsequently converted into organic ash which could be then converted into organic fertilizers and can go back into the community for the plantations. So just to give you some example in terms of what we have actually done about utilizing these organic ash and converting them into fertilizers, which are then, from our perspective, we do it as a CSR activity to help the local community to also kind of enhance their productivity in their plantations. So this is just one of a small setup to give you an idea in terms of how the ash is then converted into fertilizers. The ash management is an important aspect of any bioenergy plant. We need to take into consideration what's the best methodology to utilize this ash. One of them, as I mentioned, is to use it for fertilizers. We could, of course, then recycle it back for converting into bricks or for generating or as a byproduct in one of the in the cement plant for their processing. So we need to look at what is the best methodology to recycle this ash back again. I'm also going to take a few minutes to talk about some of the challenges that we face when we put up such bioenergy plants, and that's specifically related to the feedstock. As we know, in most of these bioenergy plants, again, depends on the geography. Different types of biomass can be used to generate thermal energy. These biomass, obviously, we need to look at what is the kind of availability of biomass, what is their size, what is the density, the moisture content, and the calorific value, and then design the bioenergy plant so that it can take care of either one of these or a combination of some of these biomass. So one of the main considerations while putting up a bioenergy plant is to actually have a biomass procurement strategy. As you know, apart from the biomass security, we also need to see that the biomass that is sourced is sustainable. We need to ensure that the availability of biomass is within a reasonable distance from the point of use to ensure that the logistic cost is at a low level and the carbon footprint in terms of the vehicles which are used for the logistic is also kept minimum. We also need to take into consideration the seasonality issues for the availability of some of these biomass. So one of the success factors for us has been in terms of building our engagement level and the kind of relationship that we have with our biomass suppliers to ensure that the security of the biomass is ensured for the long run. Supply chain challenges, as I mentioned, of course, seasonality, the availability of the suppliers. We also need to look at whether these biomass need to be stored at the point of use, or we need to create some external aggregation points to store them. Depending on the distances, we also need to have a strategy to ensure whether these biomass need to be densified before they are transported. So these are some of the challenges that we have to look at. And of course, the cost efficiency in terms of what is the availability of biomass and its moisture content and the ash content. These need to be also taken into consideration. And finally, we also need to look at the sustainability aspect, which most clients expect that the biomass that is supplied in these plants are sustainably sourced, taking care of all the compliances. So just to give you a quick update, we have currently about 15 bioenergy projects which are in the Southeast Asia region. We have almost 11 of them already running, and few of them are under construction. And these are some of the pictures of typically how a plant looks in an industrial application. So this is a plant which is a manufacturing plant for dairy products, and we have a earmarked area which is allocated where the entire bioenergy plant is put up, including the boiler, the warehouse for the fuel, and as well as the air pollution control system that is installed to meet the local guidelines. These are some other projects that we have done, just to give you an idea how these look. So in all, currently we've been able to contribute to the bioenergy setup. We are sourcing almost close to 200,000 tons of biomass per annum across all the projects that we have. Effectively, we are reducing almost about 100,000 tons of CO2 every year. and we're recycling almost close to 20,000 tons of ash back to the community, ensuring a circular economy. This is again just an illustration of how a typical plant looks and what kind of infrastructure needs to be provided to have a bioenergy plant inside an industrial process plant. So we need to get into the selection of the different kind of systems on the boiler, the flue gas treatment system, the ash handling system, the storage facility, as well as the handling system that needs to be provided. And last but not the least, I think maintaining the safety culture in any location that we work is absolutely important. And this is something that is important to the clients as well, where we install these plants. So that's it from my side. Thank you very much.
Jawahar, that was fascinating how professional you're running this energy provision to big industries. And I noticed you have very prominent brands that you're serving. So I guess these customers are very demanding also on the professionality. Now, let me ask you one thing. These brands, they are committed to reducing CO2. Are they willing to pay higher prices for the energy? So are they actually paying more after cooperating with you, or are they paying less?
So that's the $1 million question, Christian. I think while most brands have obviously made their net zero commitments, at the end of the day, when we put up these plants in specific countries and specific locations, each of these plants by themselves are obviously profit centers, and they do look at what is the economic feasibility of these projects as well. So yes, I think while we are meeting their sustainability commitments, we still need to give them some kind of a saving on the economics, which is not always possible in all locations.
But it is possible in some, at least in the majority of locations.
Yes, and typically, if the client is using maybe gas or oil, it's definitely possible. But if they're using other fossil fuel like coal, especially as you know, in Asia, many of the countries are coal producing countries, it becomes very difficult for us to match those prices.
Exactly. I mean, that's also my experience. Whenever it comes to gas or oil, bioenergy can be definitely competitive, especially when it comes to heat applications. With coal, it's more difficult. But in that case, we also have very high savings of emissions and also of air pollutants, I think you can say. There is a question here from the audience. What would be a typical cost of investing in this type of energy plant? Can you give us one example where you are able to mention the costs and the amount of energy and biomass that is being used in this project?
I think the investment is obviously dependent on a few things. What is the energy demand from the client side? What is their steam consumption? And hence, what's the size of the boiler that we need to put up? There are also specific demands which are made by customer in terms of maintaining safety compliances, etc. So we may also need to go for some certification, especially on the compliance side. I think having put together all that decides the kind of capital investment that needs to be made. But I could give you maybe some ballpark numbers that if you're looking at a steam plant, let's say anywhere between 10 ton per hour to 25 ton per hour of steam generation, the investment could vary anywhere between, let's say, $5 million to $10 million, depending on what the specific requirements are.
Thank you. That's helpful. That gives us a sense of the sizes. I am going to be the last speaker in this webinar, and I'm going to go all the way down to very small size applications, because what I want to share with you is the role of bioenergy for domestic cooking. And obviously, domestic cooking is an application that is, we're talking about 1 or 2 kilowatts of power demand. We're talking very small scale, but everybody needs cooked meals in this world. So it is a very widely relevant issue. And in fact, over 2 billion people are still using firewood to provide this heat. And as they are doing that, those persons that are cooking are often subject to tremendously high levels of air pollution, which has very heavy impacts on their health, on the health of children that are also in the kitchen, and that really create a problem. And the question is, can bioenergy provide a solution that is better than that? And this is indeed the case. Bioenergy can provide a better solution by, first of all, using a different technology of combustion, by basically gasifying the fuel, and by processing the biomass before using it. So by drying it and densifying it, for example, in the form of pellets or of dry chips. And that makes a hell of a lot of difference and opens the possibility to use biomass in a sustainable way. And I'll introduce one of the most advanced biomass cook stoves. This is a cook stove for pellets that are made from bagasse, so from sugarcane residues, and it reaches a thermal efficiency of 60%. So it's just as efficient as an LPG cooker. It's just as clean as an LPG cooker, but it is using renewable energy and is much, much cheaper than any fossil energy device, and even cheaper than using charcoal. Uses about half as costly as using charcoal. So there are really good solutions with biomass, and still people say, oh, why would you use biomass? Why don't we go solar? And if you go solar, you have to store the energy, the solar energy, because the time you're cooking is not necessarily the time when you need, when you have enough sunshine to provide this energy. And I want to show you here in this slide how storing electric energy and storing energy in the form of biomass compares. If you have 600 grams of pellets, this is enough to deliver about 1.5 kilowatt hour of delivered heat. So also already assuming the losses of heat during the combustion. And it amounts to about a cost of 12 to 18 cents. That's about the amount of energy a family would need, a family of 5 would need to cook a large meal. And if you would need to store that amount of energy in batteries, like here I have a picture of a power bank, you would need 30 of these power banks to store the same amount of energy as this bowl of pellets. They would weigh about 10 times as much, so more than 6 kilograms of metal mainly, and they would cost about $600. So that is why the storage aspect of bioenergy is relevant. It's so much easier to store energy in this form, and so much, infinitely cheaper. I mean, more than 3 orders of magnitude cheaper to store it than to store electricity. And that is why we are really strongly promoting this. There is a calculation of very recognized scientists from MIT, from Princeton, together with some Rwandan researchers, that have assessed the costs of electrifying African countries. They did that for 40 sub-Saharan African countries, looking at how much would it cost to provide an electricity grid that provides the same services as we are used to in the northern developed countries hemisphere. And they came up with a figure of about $1,200 that are needed per kilowatt of added capacity. So for a household of 5 people that would cook and would have 2 electric plates for cooking, using about 1 kilowatt each, this would amount to an investment of $2,500 into the electricity infrastructure to be able to provide this. If I compare that with a pellet plant that is providing fuel for about 50,000 households, this pellet plant will cost about $2 to $5 million, depending whether you use Chinese equipment or European or American equipment. There are really significant price differences. but also differences in reliability and things like that. So it's difficult to compare. Anyways, that's the range. The range is pretty broad, but you're talking about an investment of $40 to probably maximum $100 per household. And that compares with $2,400 per household. Pellet cook stove will cost approximately $50. So we are overall talking about approximately 20 times the investment if you want to go to electric cooking. And that's why I believe there is really a big space for, of course, eventually in 50 years, we hope that Africa will be fully electrified with enough power to provide everybody. But in the meanwhile, we can start to use clean biomass technologies to provide that same amount of service, the ability to cook meals in a clean environment in an efficient way with bioenergy. If you look at the cost per energy delivered, here are some calculations we did for Kampala in Uganda. So that's not Rwanda, but the situation is not so different. In Kampala, for example, electric energy would cost about 1,200 shillings per kilowatt hour of delivered energy, and pellets would be at around 400. So it's a factor of 3. So people would pay about a third of what they would pay if they go electric. So both in terms of investment and obviously in terms of running costs, there is a very significant cost difference. And that's why I wanted to show you the conclusion. The possibility of biomass to release high amounts of stored energy in a short period of time is a big advantage and allows to provide cooking services with a way lower costs than other technologies and still do it in a sustainable way. So that's the message. And this is all basically. So feel free to contact me, especially if you consider to become our member. And let's see if there are questions in terms of what I have been presented. How are the pellets produced and distributed, and how can the existing providers of charcoal be used to avoid them being made unemployed? Well, that's a very important question, and I think that's one of the things that really are an advantage if you stick with bioenergy and you don't transition, for example, to LPG, which is very widely promoted as a solution of choice, because imported LPG puts the entire bioenergy value chain out of business, and it is much more expensive. So, but what about the charcoal producers? Well, I think in many countries, what will happen is that biomass will be produced on purpose. You can grow fast-growing grasses that have a very significant energy output. On a hectare of land, you can produce 20 tons of dry material per year with a value of probably, well, let's say at least $1,000 or even more. So it's a very valuable crop if you think about the energy value of this biomass, and this and you can process this also in small pelleting plants, and these pelleting plants offer jobs. They offer jobs in operation. They offer jobs in logistics of bringing the biomass to the plant. They offer jobs in producing the biomass in the fields. So there is a possibility to keep up a local biomass producing sector. Fine. Cook stoves exist for years now. How is their market penetration? Yes, well, I think yes, this discussion about the clean cook stoves market penetration has been going on for a long time, and it has been to some extent unsuccessful. And the reason is basically because even the investment of $50 into a clean cook stove for an African household is too expensive. And one way of dealing with this can be carbon credits, because you get out of unsustainable biomass use if you do it in a more sustainable, in a more efficient way, and you get carbon credits. And that is one of the hopes that finally now, with the emerging carbon markets and with very strict monitoring technologies that are now available, where you can really monitor how much fuel is a cook stove actually using, how much sustainable fuel is he actually using, carbon credits will be a way to pay for this transition. We have a working group at the WBA of companies that are active in this field, and the expansion plans of these companies are quite impressive. So they are talking about projects of 50,000, of 100,000 stoves in one place. So they are really seriously looking into investing into pellet production and really into distribution of these cook stoves. But it is obviously an emerging market. It's a very young market, and will still need, of course, years to develop to its full size, but it could become really big. Use of hydrogen is gaining traction. How would the use of biomass or biogas compare with it? Well, to put it bluntly, I mean, it's a much, much easier solution, much less sophisticated, much more adapted to what we can do easily. Hydrogen is rocket science. Hydrogen is very hard to contain. It's very expensive to produce. Hydrogen is not an energy solution. It's an energy. It's a form of energy. It's not an energy production in a way, because you need electricity to produce the hydrogen. I don't see hydrogen coming up nearly as fast as all the hype about hydrogen is currently promising. The rotation time of many biomass is 1 year is mentioned. Yes, you can produce, for example, these fast-growing grasses in a very short period of time, and you recycle the carbon dioxide in a very short period of time. I think with this, we are coming to an end. I would like to thank very much to all of our presenters. I would like to thank to all of our listeners. I hope you enjoyed the session, and feel free to contact us. Goodbye.
Thank you.